Have you ever wondered what magic turns an idea scribbled on a napkin into the apps, websites, and systems that run our lives every day? What if I told you that behind every tap-to-open moment on your phone is a long, thoughtful process called software engineering? And it's both an art and a science? Welcome back to Ruby Parker, where learning meets the future, and today we're diving deep into what is software engineering. Software engineering is the discipline of designing, building, testing, and maintaining software systems with the same care, process, and rigor engineers use for bridges or airplanes. But here's the twist. Unlike bridges, software can change overnight, and sometimes that change breaks the entire bridge, and that's why software engineering matters so much. Think of a software engineer as an architect, a chef, and a detective all rolled into one. They design a blueprint, combine ingredients to build the product, and then track down bugs like a sleuth. Let's start at the very beginning. What is software? Software is a set of instructions that tells a computer what to do, but software engineering is the practice of building those instructions so they're reliable, efficient, secure, and maintainable. A single developer can write code that works, but software engineering is how teams build systems that millions of people can use without crashing. Surprising stat, modern applications are rarely a single file. They're huge ecosystems of code, libraries, services, databases, and networks all working together. Story time. Imagine Ruby wants a food delivery app. She dreams it, sketches screens, and tells a developer friend, make it work. If the friend just codes one feature at a time without plan, the app might work for one user but fail under real traffic, leak personal data, or become impossible to update. Software engineering prevents that. It turns Ruby's idea into a product that scales, protects users, and evolves gracefully. Now let's unpack the lifecycle. The Software Development Lifecycle, or SDLC, that engineers use as a map. First step, requirements. What should the software do? Who will use it? And what constraints exist? Second, design. Architects draw high-level blueprints, choose databases, and define modules. Third, implementation. Developers write code, building components and stitching them together. Fourth, testing. QA and automated tests verify that features work and that nothing breaks when you change something else. Fifth, deployment. The product goes live, often in stages, to users. Sixth, maintenance, the real marathon, fixing bugs, adding features, and keeping the system secure and fast. Plot twist, most of the cost of software happens after launch, not during initial development, so engineers focus heavily on maintainability and long-term planning. Okay, methodologies. How do teams organize the work? You might have heard of Waterfall, Agile, Scrum, and Kanban. These are different ways to plan and deliver features. Waterfall is linear. Plan everything, then build, then deliver. But in today's fast world, Agile is king. Small iterations, frequent feedback, and continuous improvement. Within Agile, Scrum gives structure with sprints and roles, while Kanban visualizes flow and prioritizes continuous delivery. Mini surprise, the method you choose changes the team culture as much as the code you write. Let's talk architecture. The big decisions that shape a system. Monoliths are single, large applications where everything lives together. Easy to start with, harder to scale. Microservices split functionality into small, independent services that communicate over networks. Great for scaling, but complex to coordinate. There are also event-driven systems, serverless functions, and hybrid approaches. Each has trade-offs in complexity, cost, and performance. Real-world comparison, building a monolith is like building a single big hotel. Microservices are like building a network of boutique hotels that share a booking platform, languages, and tools. What do engineers actually use? There's no single correct language, choices depend on the problem. Python and JavaScript are popular for their speed of development and rich ecosystems. Java or C# power many enterprise systems. C and C++ are used for performance-critical components. Rust is gaining traction for safety and speed. Front-end engineers use HTML, CSS, and JavaScript frameworks like React or Vue to create interactive UIs. Back-end engineers choose frameworks and databases to store and serve data. Fun fact, many modern apps combine 5 or more programming languages across client, server, and infrastructure. Testing and quality assurance. The safety net. Unit tests check individual pieces of code. Integration tests check how parts work together. End-to-end tests simulate real user behavior. Automated testing is the unsung hero. It prevents regressions and gives teams the confidence to ship quickly. And then there's code review, a human inspection that finds logical errors, improves style, and spreads knowledge across the team. Dramatic reveal. Some production bugs come from assumptions nobody wrote down, not from syntax errors. That's why tests and documentation matter so much. DevOps and CI/CD, making releases reliable and repeatable. DevOps combines development and operations, automating build, test, and deployment pipelines. CI/CD, so changes move to production safely. Continuous integration means merging code often. Continuous delivery means your code can be released at any time. Continuous deployment means it's automatically released if it passes checks. Cloud platforms like AWS, Azure, and GCP make running services easier, but they also introduce new responsibilities: cost management, security, and observability. Real-world relevance. Every time a popular app pushes an update without your notice, that's CI/CD and DOVPS at work behind the scenes. Performance and scalability. What happens when your idea gets famous? A feature that works for a few users may choke under millions, so engineers plan for scaling. Horizontal scaling, add more machines, and vertical scaling, make machines stronger. Caching, load balancing, and database sharding are common techniques. Measuring latency and throughput helps prioritize optimizations. Quick question, have you ever noticed an app slow down during peak hours? That's a scaling problem engineers try to solve in advance. Security and privacy, non-negotiables. Software engineers must protect user data, prevent breaches, and defend against attacks. That means encryption, secure authentication, least privilege access, and regular security audits. Ethics also comes into play, handling user data responsibly, avoiding harmful algorithmic biases, and designing for accessibility and fairness. Shocking but true. Many breaches happen due to simple misconfigurations, not exotic zero-day exploits. Structure and discipline prevent these. Design patterns and clean code, making code human-readable. Design patterns are repeatable solutions to common problems. Singletons, factories, observers, they're like templates that experienced engineers recognize. But patterns without understanding cause over-engineering. The best engineers balance practicality with principles like SOLID and KISS. Keep it simple, stupid. Code readability matters because the majority of time is spent reading and modifying code, not writing it for the first time. Real-world examples. Walk with me through a few familiar systems. Social networks. They handle user profiles, feeds, notifications, content moderation, and billions of concurrent connections. Each feature is a distributed system by itself. E-commerce, inventory, checkout, payments, fraud detection, and recommendation engines must all talk to each other and remain reliable under heavy sale traffic. Medical software must be accurate, secure, and compliant with regulations. Mistakes can have life or death consequences. Mini surprise! The same core software engineering practices apply across these domains, but the priorities and constraints differ wildly. Careers in software engineering. What paths exist and how to grow. You can be a front-end engineer crafting delightful UIs, a back-end engineer building APIs and databases, a full-stack engineer doing a bit of both, or a machine learning engineer building intelligent models. There are also site reliability engineers, SRES, who keep production systems healthy, security engineers who protect systems, and product managers who translate user needs into roadmaps. Career growth often moves from individual contributor to tech lead, then to architect or engineering manager. Or you can become a specialist in an exciting niche. Pro tip, the strongest engineers combine technical depth with clear communication and empathy for users. How to become a software engineer. Practical roadmap. Start with fundamentals, learn one programming language well, understand data structures and algorithms, and build small projects that solve real problems. Contribute to open source, join internships, and practice coding interviews. But also build a portfolio that shows what you can create, not just what you can pass a test on. Learn version control, JIT, testing, debugging, and at least one cloud platform. Remember, projects teach you more than theory alone. Encouraging note, you don't need a computer science degree to succeed. Curiosity, persistence, and practice take you far. Tools and resources, where to learn and practice. Online courses, coding bootcamps, documentation, and community forums are valuable. But so is building things for friends, small businesses, or yourself. Read other people's code, review pull requests, and ask for feedback. The fastest way to improve is deliberate practice with real constraints. The human side, teamwork, communication, and culture. Software engineering is social. Code is written for people to understand and maintain. Effective teams communicate clearly, document decisions, and prioritize psychological safety. Mistakes will happen. Teams that learn from failure and iterate quickly outperform those that blame. Fun fact, some of the most innovative features come from cross-disciplinary teams where designers, engineers, and product managers brainstorm together. The future, AI, code generation, and changing roles. AI tools can already generate boilerplate, suggest fixes, and speed up development, but they don't replace human judgment, architecture, or ethics. Rather than replacing engineers, AI is shifting what engineers do: higher-level design, verification, and integrating AI safely into products. Imagine a future where writing a prototype takes hours instead of weeks, but verifying safety, fairness, and privacy will remain critical human tasks. Question for you: would you trust an AI to write code that manages your bank account? That's the kind of ethical decisions software engineers will make more often. Common misconceptions. Let's bust a few. Myth: software engineering is just coding. Reality: coding is a piece of a larger discipline that includes design, testing, and maintenance. Myth: you must memorize every algorithm. Reality: understanding concepts and when to apply them matters more than rote memorization. Myth: good engineers never have bugs. Reality: everyone has bugs. How you respond and learn defines your skill. Practical mini challenges to try right now, tiny, actionable wins. Build a simple CRUD app. Create, read, update, delete. It teaches you databases, APIs, and UI basics. Add automated tests to an existing project and measure how it changes your confidence to refactor. Deploy a small app to a cloud provider and watch traffic spike. Even to a handful of users, the lessons are huge. Story close. Why this all matters to you. Software engineering shapes the tools we use to learn, work, and connect. From the phone in your pocket to the safety systems in hospitals, and the algorithms that recommend what you watch next. By understanding how software is built, you gain power as a user, creator, and consumer. You can build responsibly, demand better products, and make smarter career choices. Dramatic reveal: the software shaping our future is built by humans, and with the right tools and mindset, you could be one of those builders. Final motivational outro. Let's wrap this up and light a spark. If you enjoyed this deep dive and want clear, friendly lessons that turn complexity into action, smash that like button, drop a comment with your toughest software question, and hit subscribe so Ruby Parker can keep bringing videos like this. Tell me in the comments, what part of software engineering surprised you the most? Architecture, testing, security, or the career paths? I'll read and reply to as many as I can. Remember, every great app started as a curious idea and one person who decided to learn. You don't need to be perfect, you need to start. Thanks for watching Ruby Parker. Stay curious, keep building, and I'll see you in the next video.